Okay, back to chapter 11, the gas laws. What we talked about last time were Boyle's law. Boyle's law is pretty straightforward. It says that if you apply pressure to a gas, the gas compresses. In other words, the volume of a gas is inversely related to pressure. If you wanted a mathematical statement of Boyle's law, you find it in the book here. It's right here where it says P1V1 is equal to P2V2. What's with the P1 and the P2? Oh, that's the initial pressure, the final pressure, the initial volume, the final volume. So in this little representation here, P1 is 1 atmosphere. The final pressure is 2 atmospheres. The initial volume and the final volume. So that was Boyle's law. You don't have to worry about this equation here. You'll see why a little bit later in this video, why you don't have to memorize that equation. But you should know Boyle's law, that basically when you put pressure on a gas, the gas will contract. We talked about Charles' law. Charles' law says when you heat a gas, it expands. So we had this picture here from the book. Here's your gas sitting in ice water. Your gas filling a balloon sitting in ice water. Take that same sample of gas and heat it up, and the gas expands. So Charles' law says that the volume of a gas is directly related to temperature. If you increase the temperature, you will increase the volume. So you increase the temperature, you also increase the volume. That's a direct relationship. Now, mathematically, here's your equation. The initial volume, the final volume, that's your initial volume, your final volume, your initial temperature, your final temperature, that would be the temperature of the ice water, the temperature of the boiling water. And again, don't worry about memorizing that equation. You're not going to need it, and you'll see why later. We talked about Avogadro's law, which says that the volume of a gas is dependent upon how many moles of the gas are there. Now we're going to do some number crunching. We're going to work a problem using the so-called ideal gas law. The ideal gas law is this guy here. Pressure times volume equals moles times temperature times R. What is R? R is the gas constant. It's a physical constant. Happens to be this number here. It's 0.0821, so R is 0.0821, and it has some weird units on it. It's liters times atmospheres per mole times Kelvin. Now, when you go to use this equation here, what you're going to plug in for R is just this. You plug that in for R. Don't make the mistake of trying to plug in a number for atmospheres. Don't try to plug in a number for Kelvin. These are units that go with this number, and these units will end up getting canceled out. So you're not trying to plug something in here or plug something in here or here. You just leave those units and you'll see they'll all cancel out. So what's the ideal gas law for? Well, it interrelates 4 different variables. If you have a sample of a gas, the gas is at a certain pressure. That gas is going to be at a certain temperature. It will have a certain volume, and it will contain a certain amount a certain number of moles. Those four variables are all related through this equation. Now, when you're using this equation, it's crucial you know this. When you plug pressure in there, pressure has to be in the units of atmospheres. When you plug in volume, that volume has to be in the unit of liters. Temperature, anytime you do anything with a gas, the temperature has to be expressed in Kelvin, the absolute temperature scale. So temperature has to be in the Kelvin scale. So when you're using the ideal gas law, watch your units. Pressure's got to be atmospheres. Volume has to be liters. Temperature has to be Kelvin. So, simple example here of using this equation. Let's say you have a sample of oxygen gas and it's taking up this much space. So you got a container that's holding 28.5 liters of oxygen. And that gas happens to be at a pressure of 1.8 atmospheres and a temperature of 25 degrees. Hey, how much oxygen is that? Don't say, oh, it's 28.5 liters of oxygen. No. How much oxygen is it? That means how many moles of oxygen are there. So, how do you work this? Oh, N, in the ideal gas equation, N represents the amount of stuff, moles. Remember, moles, that's the unit we use to represent how much of that chemical is there. So this one wants you to find moles. Well, you use the ideal gas law here, PV equals nRT. It's asking us how many moles are there. Hey, we're trying to solve for this variable right here. That means we want N to be living all by its lonesome on one side of the equal sign, which means I got to get rid of R and T. How do I get rid of R and T? I divide by them. That way, R cancels out, that cancels out. Well, if I divided this side of the equation by RT, I have to divide the other side of the equation by RT. So we've now solved it for N, and I'm going to flip this around because my brain works better if I'm reading the equation from left to right. So N, that's moles, that's that guy, is equal to PV over RT. We just plug in what we know. The pressure, our oxygen gas is at a pressure of 1.8 atmospheres. It's taking up how much space? What's the volume? Oh, 28.5 liters. It's at 25 degrees, which I showed you up here how to convert from Celsius to Kelvin. So 25 degrees Celsius is 298 Kelvin. So our temperature here, for temperature, we'll use our 298 Kelvin. And what do we plug in for R? All this is what we plug in for R. So R is going to be 0.0821 liters times atmospheres over mole times Kelvin. Now, notice I didn't try to plug in a number here for liters. Oh, because it's just, that is just there to make all the units work. Notice I have liters on the bottom of this big fraction, liters on the bottom, liters on top, liters cancels out. Atmosphere is on the bottom, atmosphere is on the top, it cancels out. Over here I have Kelvin, and here I have Kelvin on the bottom here, so Kelvin cancels. The only unit that didn't get canceled out is moles. So if we run this one through our calculator, we did our 1.8 times 28.5, and we divide by this number, and then we divide by the 298, we'll end up with 21 moles of oxygen. So if you got a container with this volume, this pressure, this temperature, and it's holding oxygen, it is holding that much oxygen. And that's the ideal gas law. Again, it's just an equation that relates these four variables for a gas: moles, pressure, volume, and temperature. One more type of problem to work with the gas laws, that would be initial final state problems. We're talking about using the so-called combined gas law here. We're going to skip the STP part. We talked about that last time. The combined gas law is this guy. So that's P1V1 over N1T1 equals P2V2 over N2T2. What's that good for? Anytime you have a gas and you change the conditions that it's under, you apply some more pressure to it, or you heat it up, or you expand the volume of it. Anytime you're changing the conditions for that gas, if I change the pressure, I'm also going to change the volume. If I change the temperature, it's going to change the pressure, and it's going to change the volume. So anytime you're changing things, we call those types of problems initial final state problems. And when you're doing that, you use this equation. Now, when I told you not to worry about the mathematical statement of Boyle's law and Charles' law, it's because they're built right into here. This is Boyle's law combined with Charles' law, and also combined with Avogadro's law, all in one package. So let's show you how this works. One thing to know about the combined gas law: if you have a variable that did not change, you just take it out of the equation. If a problem says, hey, the pressure was held constant, we changed the temperature and the volume, but we didn't change the pressure, then you just ignore pressure. Take it right out of the equation, plug all your variables in. If it says temperature was held constant, you just ignore temperature, plug everything else in. So it's a really easy equation to use. Let's take a look at a problem. You have a sample of gas. That gas is in a cylinder, and it's compressed from 6 liters and a pressure of 2 atmospheres. So this would be your initial volume. So it's from a volume of 6 liters, it's compressed down to 3 liters. So you're starting at 6 liters. That's your initial volume. You're compressing it to 3 liters. That's your final volume. It started off with a pressure of 2 atmospheres. So 6 liters and a pressure of 2. Hey, that's P1. What is the pressure of the gas after it's been compressed? They're looking for P2. They're looking for the final pressure. So what you're after here is P2. And this problem says, hey, the temperature is held constant. So you're not changing the temperature. Okay, it's an initial final state problem. You'd use your P1, V1 all over N1, T1. That's equal to P2, V2 all over N2, T2. Let's see, it says the temperature is held constant. Hey, if temperature is held constant, we don't have to worry about temperature. It's a sample of a gas trapped in a cylinder. So you're not pumping any more gas into it. You're not taking any gas molecules out of it. The number of gas particles doesn't change. We can ignore moles. Suddenly this equation becomes P1 V1 equals P2 V2, and that's Boyle's law right there. So all we got to do is plug in the numbers. Our initial pressure is 2 atmospheres. Our initial volume was 6 liters. We're looking for the final pressure. That's what we're trying to solve for. The final volume was 3 liters. All you got to do is solve this for P2. So your P2, your final pressure here is going to be your 2 atmospheres times your 6 liters. And you're going to divide by the 3 liters. And P2 is going to be 12 divided by 3 is 4. So the final pressure is 4 atmospheres. That's about it for the gas laws, guys. Next video coming up will be nuclear chemistry. I might try to do that in one big video. Hope it doesn't put you to sleep. And that will pretty much be the end of the class at that point. You all take care.